So the basic idea is this. In order to come up with a volume of a three-dimensional object, what you need to do is you need to have whatever the function is, and from that function, you need to do the picture, find the solid, etc. But what you basically need is the area of a particular cross-section of that surface, and then multiplied by dx, or if we do it the other way, if we get the area as a function of y, multiplied by dy. That's how we get the volume. That keeps it completely generic. And of course, we would have the limits that would depend on how far we're going with this. With functions like the parabola, of course, it's infinite. I have to say it has some particular space where I'm going to look at, between 2 and 6, or between 4 and 8, or whatever that might be, because if I want to get the volume for the whole thing, I can't get the volume for the whole thing. It's infinite, all right? But this is the basic approach that we take. Now, for those cases that I've looked at so far, all of them just form circles. And that's good. But when you rotate things around an axis, that's what you form, is a circle. However, we could change this slightly. We can say, let's look at the function y equals the square root of x. But I'm going to look at this domain from 1 to 3. Now I go 1 to 4, because that's nice to take the square root of x is then 2. Okay, so what does that look like? Now, in general, that function looks like this. Sideways parabola. But I'm saying I'm only going to look between 1 and 4. That means this part of the function is not there. That means that the function stops right there. When I rotate this around the axis and get a mirror image down here, it's going to look like that. But there's nothing back here. That means what's going to be formed is it's going to form a hole down the middle. Okay, we're only looking from here to here. Okay, that is only defined from there and over to here. And so in the y direction, whereas that's in the x direction, y is then going to be 1 to 2. That's the only place where this function is defined. And so as a result, when I rotate that around, instead of getting the whole bullet, I'm going to get a bullet with a hole down the middle of it. So a little bit different in terms of what I'm looking for here. I still did the same thing in terms of I rotated around this axis. If I draw a perpendicular to that, so this is where I made the slice, like this. And so that's still delta x. That tells me I'm going to want to integrate this with respect to x. But if I take that slice out and look at what it looks like, it no longer looks like just a circle. It's a circle with a hole in the middle of it. It's a ring. Right? So now I look at that and I say, well, this is a little bit different than what I did before, because before all it just said area is pi r squared. That's true, okay? But now I can say the area of the big circle is area of the big circle is pi big R squared. And I can say the area of the little circle is pi little r squared, where I would say this distance right here is r, this distance right here is big R. And so if I want to know the area of this region right here, I would take big area minus little area. So the area of that region that I'm interested in would be pi big R squared minus pi little r squared. So I look at this and I say, well, what do I know about this? Do I know big R? Do I know little r? Well, big R is a changing distance, right? In this case, because here big R is bigger than it is back here, etc. Big R is related to the function. What about little r? Both of them are in the y direction, okay? This distance from right here to here is not changing, right? That started because we said we're only doing from 1 to 4, and that led to only 1 to 2 in terms of y, right? So that distance right there isn't just y or r or anything like that. That radius right there, little r, is 1 the whole way, and it doesn't have to be. We could have a different function underneath which would make this different, but for our purposes right here, that r is 1. So I know that. What's big R? Big R, well, that's some y direction. But of course, because I did delta x, I want dx, I want everything in terms of x. Therefore, I look at this and I say, well, what is y in terms of x? Well, I know that. Y is that, square root of x. So when I go to this area, and again, I can do some work with this before I even get into the integral, r squared is going to be just x, minus pi times 1 squared, which is going to be just pi, and I can do that as well. Pi into x minus 1. So, now I say I'm going to form my integral. I need the area. I'll bring pi outside and just say I got x minus 1 dx. Integrated from where to where? Well, I'm talking about the x integration. I'm adding up all of these slices from here all the way up to there. And I said x starts at 1, x ends at 4. So, again, the integral itself is simple. Raise the power by 1 and divide by it. I have pi. 4 squared is 16. That means I've got 8 minus 4. Minus, and plug in the 1, I've got 1/2 minus 1. So it appears that I have pi, and I have 4, and this is going to give me plus 1/2. Right? Or we could call that 9 over 2. So I've got 9 pi over 2 is ultimately the answer that I get here. And that's giving me the volume. Again, if you think about what does this look like, okay? It's got, it is this piece, but with a hole down the middle of it. It looks like a bullet that you've drilled a hole right through the bullet. Okay? So we're talking about the volume of that outer shell.